Cool, thanks for having me. It's good to be here, and it's really cool to be able to do these in person again. So yeah, thanks to CA for putting it all on. So as mentioned, yeah, I'm James. Definitely recognise a fair few faces in the room. So let's kick into this. So here's me and Glenn Tanner where we fly the Mark II, which you can see there. So yeah, that's my name. So I started at BE and MEC. Then I worked in various 145, 146 and 148 organisations. So as mentioned, started at Flight Structures. Actually did a lot of work with the Air New Zealand and Altitude team during that time. And Airwork, then went over to Airwork and got pretty involved in the 145 and 148 there as well. Then became a DDH in 2015 under Airworks 146. It actually recently lapsed like a week ago. And I haven't been using it a whole lot, so I didn't proactively renew it, but been trying to keep up to date with everything anyway. Co-founded Dawn Aerospace. Right, so the main thing I got asked to talk about was Part 102, which I put this up here because we've all seen rules before, so it's not too scary. It's a rule, like you've all seen plenty of times before. But once we get through all this, I can have a bit of a show and tell about Dawn as well. So 102, and this is really high level and pretty introduction, so this might be really familiar for lots of you. But anyway, it's quite interesting in that in many ways it's a rule that aggregates operations, design, maintenance, manufacturing, just about everything and anything that you could need to operate your remotely piloted aircraft. Now, this means that it's very, very empowering because it's all of these things, right? It lets you do a huge amount, obviously depending on what's in your exposition, but conceptually it's very broad in its capability. And empowerment is awesome, but it's a double-edged sword, as many of you have probably come across with flight performance-based rules and latest bits of Part 23 and so on. There's a lot to figure out when you have something so broad and performance-based. But this also really presents an opportunity, and this is the main kind of point that I want to drive home today for this group, because the last one really strong theme that I picked up from the last one of these that we had in person a few years ago was that the 146 environment was stagnant in many ways, and that it wasn't growing a lot. There wasn't a lot of new development. There wasn't a lot of new people entering it. Weren't a lot of new delegates coming along and so on. But this, I think, really presents a substantial opportunity for the industry to grow significantly and do some pretty exciting stuff. So this, how do we figure things out and how do we make this happen? This is where really all of us in the room come in. So, quick overview of how lots of 102 from a design, but also manufacturing maintenance kind of gets implemented. So it starts with this thing, JARA SORA. So SORA is doing a specific operational risk assessment. So the components of that, so first you do your CONOP, what are you going to fly, how are you flying it, what's the purpose, all that sort of thing. Next, broadly, you assess your air risk. So when you're flying this thing around, how much risk are you presenting to the rest of the aviation system in the air? So are you interacting with other aircraft? Are you potentially going to have a collision with someone? That sort of thing. Next is your ground risk. So if you fall out of the sky or something doesn't go quite right, what risk do you present to the public on the ground? And then from that, you get to the sales, specific assurance, and integrity levels you need to achieve, and there's a bunch of operational safety objectives that you go through. Now, depending on your air risk and your ground risk, that really determines how thoroughly you need to work on these sales and OSOs. As I'm sure you can all appreciate, if you're operating in the middle of the Pacific Ocean, there's no one around, and you're below 400 feet, you probably can't really hurt anyone if you tried. So, your integrity and those sorts of things can probably be relatively simplistic, whereas if you wanted to fly a very heavy, very fast, very complex aircraft over Auckland or over, during an air show or something like that, then, we probably want to be pretty careful about that. And so what is quite good with this, though, is it gives you a lot of flexibility in terms of, are you quite risky, therefore you need to be really careful? Are you not very risky, therefore you can probably have quite a bit of liberty in what you do? And there's just a link there for all the documents and so on, so it's all published online. Right, so operational safety objectives. So this requires a bunch of knowledge in order to implement and achieve these about the aviation system. And this is, again, where I think everyone here can really come in and help. Because you've all got really good knowledge about the aviation system, and for various reasons, the environment and industry of remotely piloted aircraft, drones, and all that kind of thing, there's a lot of people entering that who've got very little or no aviation experience whatsoever. And so they don't know what good practice is. They don't know what good procedures are. And as you all will be very well aware, good practice and procedures is really core to doing well in aviation. So it's something important you can bring. Even things like training, like how do you do good training? How do you audit yourself? How do you handle being audited by CAA? What's the quality management system? How do you make sure that what you build, what you operate is going to be done well? How do you do design? Don't need to explain that at all to any of you. Manufacture, same thing. Maintenance, again, I'm sure you're all very familiar with these. Operations, perhaps this is something that we're not all super familiar with from the design space, but I'm sure still a lot more than some real new entrants. Even just basics, like how do you write a compliance report? So all of these, a lot of these, I think probably a lot of you are very, very familiar with and feel like you could work on pretty confidently and come up with something that CAA's, gonna be able to interpret at the very least, and likely to be much more comfortable with than if just some new guy who's bought a DJI turns up in Wellington. Being a fit and proper person, like what does that mean? What is taking on responsibility, and how do you do that well? A whole lot more. Okay, so just some examples of OSOs. So a lot of the stuff that I'm going to go through now, I'm sure for a lot of us here, is going to seem really, really basic. But again, I just want to highlight, when you don't come from the aviation system, these things aren't necessarily obvious. And this, again, presents, this is a substantial opportunity for us to help out the industry. So the specific way that I think potentially this could be implemented is that 146 organizations can start acting as consultants. Lots of 146 organizations are consultancies, can be consultants for prospective 102 operators, where they want to write an exposition, they want to submit it to CAA, they want to show how they can do all of those things, potentially design, manufacture, operate, maintain an aircraft. And a 146 can potentially be a competent party to validate how these things are done. Cool. Just a quick reminder. So get through what some people would call boring paperwork, but I think most of us probably actually like a lot of that paperwork. So when you get to go flying. So it's really important. That's cool. Okay, so another example. So this is one of the OSOs. So your UAS, so your unmanned aerial system, is manufactured by a competent and or proven entity. And within the OSOs, you have these things called level of assurance. There's low, medium, and high. Your risk determines whether you've got to be low, medium, or high in these various categories. But now, if you're low, you need to be a standard considered adequate by a competent authority, i.e. CAA, for how the thing is manufactured. Now, if you have no idea about manufacturing, you're going to not be able to assess whether your thing or whether your methods are likely to be considered adequate by CAA. Now, a lot of you, especially everyone who's worked with a 148, you're going to have a really, really good idea of what is an adequate standard. So hence you can provide really good guidance to these people wanting to become 102 operators. Conformance, again, basic term, but a lot of people outside this industry aren't going to know what that is. And manufacturing procedures, again, and what I'm trying to emphasize here is there's stuff within these that you need to demonstrate in order to get a 102 license, which for most of us in the room, I think are going to be pretty straightforward. But for a lot of the people entering the 102 industry and aiming to get a 102 license, these things are really, really foreign. And that makes CAA's life really hard because they're having to tell people what conformance is and they're having to illustrate, how you manufacture appropriately and so on. And what I would hope for the future is that CA's life gets a lot easier by industry providing better data, better applications to them in the first place. The benefit for industry is that this is a massive new industry that it's therefore an opportunity, like a business opportunity, commercial opportunity. And then recurrency and so on. Again, familiar for us, but not for others. All right, another one. So maintenance. So maintenance is well documented. I'm sure everyone here has written an ICA. The maintenance program is developed in accordance with an acceptable standard. Again, I'm sure you all know the relevant parts of 29 or 25 or 23 or whatever, where you would use as a starting point for your maintenance program. And then that's got to be validated as well. Now, CA can do this for you, but then, potentially as well, as a consultancy, you could propose that you provide some competence in this. And CAs, I'm reasonably sure, but this is certainly a guess from my perspective, but I'm sure CA would be more encouraged accepting something from a 146 organisation than they would from a random person off the street. Okay, so why bother with this? So I'm sure it's pretty hard to argue that remotely piloted aircraft are getting increasingly more popular, therefore it's growing, therefore it's a bigger and bigger opportunity on the horizon. A lot of these may be pretty small or simple and therefore have the low integrity levels from the OSOs I've just shown, but in all likelihood this is going to get higher and higher. And especially as the designs, the programs people are working on here get bigger and bigger and more complex. The stuff Merlin's doing, Dawn's doing, Kia, if any of you are familiar with them, Whisk, I'm sure a lot of you knew. These are big budget, they're exciting, there's a lot of really ground up design, there's a lot of just really, really cool engineering work with these. So I think it's actually just really, really good work. And as I mentioned, hopefully it helps CAA out. We all have a better time when CAA is having a better time. Cool. So that's a super quick intro to 102. And now just a bit more on Dawn. Oh, okay. So this is supposed to be a globe with with a bunch of flight routes on it that are orbital, and the point is you can just easily book a flight. You can fly from anywhere to orbit, but not quite right. Anyway, so the most relevant aspect of Dawn to most of the people in the room, so our spaceplane parts of the business. So what this really is, in the simplest sense, is an aircraft capable of non-atmospheric flight. Also, it keeps the pilot on the ground, but whenever you think about anything about this aircraft, and lots of people ask like, oh, how does it do this? How does it do that? What about that? Almost always the answer is like a regular aircraft, except it's a rocket engine, not a gas turbine or whatever, and the pilot stays on the ground. Everything else, the principles more or less are the same. So what this translates to, I had to give them my presentation this morning because it was massive because of the videos in it, and some of the graphics just haven't come through, sorry, so you have to do some imagination. But anyway, it takes off horizontally, lands horizontally, it flies a suborbital profile to space. It fully integrates with airspace, so a conventional rocket, you shut down airspace because it's launching a missile, and missile's pretty dangerous. The Mark II that we're flying now, this is a technology demonstrator for our next aircraft, which will be the Mark III, which is more or less a scaled up, larger version, which has payload capacity to carry a second stage, which it then deploys at the near the apogee of that suborbital profile, and then second stage flies to space, to orbit. It's intended to be completely reusable. Again, how do you fly a normal aircraft? You go fly, come and land, put more fuel in it, off you go again. And it's designed to be agnostic of the airport that it flies from, so that this is something you can deploy globally very easily. So there was an image of the plane here, but you'll have to imagine that. This is in the avionics bay up in the front, but there's redundant power distribution, redundant C2 links, so C2 is command and control. It's a composite airframe primarily, titanium nose cone, real-time FPV downlink. This is pointing at the tail now with its camera. Has navigation strobe position lights. Again, how does an aircraft do it? Just like, how does Dawn do it? Just like a regular aircraft. Redundant electrically actuated control surfaces. Gas turbine or rocket propulsion. Electrically actuated landing gear. ADS-B in and out. I think we were one of the first, if not the first, remotely piloted aircraft in the country to have a properly certified TSO ADS-B out system. Barrow gyro magnetometer, GPS, all your kind of standard IMU and sensors and all that kind of thing. This is our ground station where we operate the aircraft from. So we've got pilot instruments in the middle, the HOTAS controls, so hands-on throttle and stick controls, backup controller. So like redundancy is a really, really important principle through everything that we build so that we maintain a good level of, well, you'll know what redundancy is for. So we have the primary HUD for the pilot, which I'll show you a screenshot of soon, backup HUD, and that's all fed from a completely independent system. Then we have the navigator station on the right. They kind of help out with the flight operations. Have a traffic monitor there, so that's where we have effectively, it's your radar. So it gets ADS-B in and FLAM and a bunch of other stuff, so we know where everybody else is. And then we have the flight director on the left. Have an additional display, which typically is just another moving map with other aircraft and stuff on it. Everyone's on an intercommunication system, including all the crew externally. So often we'll always have crew external to the trailer as well, monitoring airspace and so on. And so everyone's just on a duplex system, so we can all talk. And then we have some flight engineer stations for, if we're testing some really new equipment or something and we want to have really, really close specific monitoring on a particular system, then we'll set it up that we've got real-time data on that, on the extra displays, and engineers to monitor all that. Outside, there's a whole ton of antennas and stuff for radio links and all that kind of thing. And then there's also a UPS system, so again, everything's redundant and well looked after. Now we can also use this as a simulator, so we use it for all our crew rehearsals and so on. We have a separate simulator as well, but yeah, being able to do sims and stuff is really, really important for technology development, but also crew training and mission training and all that kind of thing. So I'm just going to see if I can pause this. Yeah, cool. Okay, so this is flying downwind, then onto finals, then downwind-based finals for a pseudo-rocket-powered landing. So this was one of the last flights we did with the Mark II with gas turbines on it. So we effectively flew a pseudo-rocket-powered profile where went to the end of the runway, went hammers down, climbed as steep as we can, go right back to idle at the top, and then just glide the whole way home. So so it has a split rudder for energy management. So use split rudder and so on to do our return to base. And so as we go through this, you'll hear the crew talking through various points on approach. So you have, airspeed, altitude, and position targets for downwind base and final. And you'll hear crew talking through that as we go.
Speed is leading back 2150 feet, so you're now at 0.3. 100 feet, 95 knots. So just remember it's going to take a little bit more to round out. Halfway through to turn, 17. And the gear well when it does. Copy. 20 knots, gear's good. Turns looking good.
So the gear pull, so gear's down and good.
500 feet, 130 knots. 200 feet, 130 knots. 5 knots. 65. That's right.
Cool. So this is a view, not from our actual sim, because I can't show you it because of IP stuff, but kind of get the idea. The sim is in case it's not obvious, it's built to like very, very accurately reflect flying it in the real world, so that the aircraft behaves exactly as it should. Therefore, the crew can train to fly it just how they will in real life. So that, and we use this extensively for crew training, but also for mission planning and mission rehearsal and so on. So that by the time we go and fly an actual mission, the entire crew should be very, very familiar with everything that's going to go on. And also have practiced, the anomalies that we might expect, and so that we can feel as comfortable as possible with managing those anomalies and responding to them in the most appropriate way. But essentially, this is more or less what the pilot sees when flying the real thing as well. Just instead of a computer-generated background, it's the video feed from the aircraft. But you've got all your standard things on here, so like attitude, heading, airspeed, mark, all that kind of thing. This is our pilot instrument system. So again, it's slightly different to the real thing. But so starting on the bottom left, so standard instruments, airspeed and altitude and so on. Then instead of your kind of typical HSI, so we have, we just call it the ball, but this is much more usable when you have very, very high pitch angle flight. So, if you're ascending at 80, 85 degrees, 90 degrees, you start getting like, yaw and everything starting to act in kind of pretty different axes and so on. So this lets you visualize things much, much better. And then there's just fuel gauges and things like that at the top. And then on the right, so the yellow line is our geofence caution. So that's our kind of nominal operating area. And then if we get to that, that's mission abort. And then the red is the area that we've established that we absolutely should not be going out of. And then the other aircraft you can see on there are just other aircraft from ADSB. And you can see you might be able to see, there's a small green line on the front of every aircraft. So that's the predicted trajectory of all aircraft. Now, there's another version of this that I can't show you again because of IP, but it's our traffic management system. And just kind of thought it was a cool thing to talk about because it's, I think it's a good example of like this working on this kind of stuff. There's so much really, really awesome, really, really cool, very, very forward-thinking stuff you can work on. And I think a lot of us as engineers find that kind of thing really exciting. But in our traffic management display, so it kind of looks similar to the other side, to the right-hand side, except you can overlay your airspace map, like a Google Maps type simplified version of the world around you, or a photo, satellite imagery as well. So, this helps with situational awareness. It takes a feed from ADSB, FLAM, like our own internal ADSB, FLAM, flight radar, and you can manually input aircraft as well. So if anyone isn't on ADSB, they've got some nice composite radar transparent aircraft. You can still manually insert these. So if a remote observer says there's someone out there, they haven't got their ADSB on, they're at 3,000 feet, 10 miles heading east, you can input that, and then it will keep it'll keep it moving with the trajectory that you've established. And this massive, so you've got a very, very good situational awareness now. And the other thing it shows relative altitudes of everybody. So if you've got a height offset of 50,000 feet or 10,000 feet, you're much less concerned with going past each other than if you're at 200 feet. And so again, this helps by giving really good visualization of this. It helps reduce crew workload because you can see immediately like, oh, that aircraft's red, I need to do something about it. Or that aircraft's green, I don't need to worry about it so much. Then also what it gives trajectory prediction for everyone. So if you're heading straight for each other and you've got a closing speed of 500 knots or something, you're really going to need to do something about that very early on. If you're quite near each other but you're going away from each other, again, you don't really need to worry about it unless both of you turn in a great hurry. But again, this allows it allows the system to really do a lot of the work for you to reduce your workload and therefore let the crew focus on the stuff that's really important. Now, all the data and all the information is always there, so the pilot can still, the pilot and the navigator can still act very, very independently of this, that even if you weren't getting a caution enunciator, you can still see, when you're pretty close to people and so on. Cool, so Dawn, Dawn's planned this map that didn't come up, but this is like a massive long-term project, right? It's decades of work, and you can't pay for decades of work up front usually. So one of the really important things that strategically has always been a part of Dawn from day one is that we get to revenue products really, really quickly. And the first stage of that for us was satellite propulsion systems. So in providing space transportation broadly, we need to be able to do in-space transport as well, and satellite propulsion is the main part of that. So here you can see a couple of our main satellite propulsion products. So this is on track to be the most popular green chemical propulsion in space by the end of next year. So 33 engines in space at the moment. That's obviously nothing compared to aviation. But the current leader's been building their engines for 20-something years, and we'll catch up to them and pass them within about 3 years. There's currently 17 million in backlog and orders for these, and about 120 million in pipeline that we're negotiating. It's a very, very enabling technology for our customers, so we can sell it at a really good price, but still make plenty of margin on it. This is flown on all the major rockets that the Western world use. So why are we winning? So there's a few important aspects of building a propulsion system. So reliability has got to be really, really good. Your thrust has to be really high, because otherwise you kind of just really slow to move around. Toxicity, historically no one cared, but now, health and safety and all that kind of thing, it's just very expensive. But the main thing actually for Dawn is that we can build this super fast. So we put a lot of effort into making our system, the way we do engineering, the way we build and develop new products, almost like Lego bricks, that we've got this engine and this control system and these tanks and these feed systems and so on. And depending what you want, we can just take these blocks off the shelf, put it together very, very quickly. Now, these sort of principles that have, really helped us to get this lead in satellite propulsion are exact same principles that we apply to launch. That what we're doing, it has to be fundamentally miles better. It's not 10% better. It's not 20% better. It's not twice as good. It should be orders of magnitude better than the alternative. And that's the aim. That's where we're hoping to get to with that. Takeoff. So when we first started flight testing, all of our flying was really relatively close proximity, and it was really exciting and cool seeing the aircraft whiz past all the time. And now it's real boring, because you see this and then the aircraft's gone until the end of the mission, and then it comes back and lands. That's the main engine for the Mark II. Very early on doing some testing at Wigram. That's the aircraft, and it's all up flight config. That's it in flight. It's another picture, just taking off and departing. It's a picture just way out among the clouds. So just coming overhead. It's not the whole crew by a mile, but it's some part of the operating crew down in Glentana. Yeah.
Compared to sort of like home-built aircraft, the level of regulatory responsibility of the 102 space is more.
It's very, very different, and this has been an interesting thing to discuss with CAA, because home build is extremely flexible, right? And Dawn certainly does not have anywhere near that level of flexibility with what we build and how we build things and so on. So
they're probably more rigorous than guys like that.
Yes. Yeah, definitely. Yeah. certainly for us. Yeah. Mm-hmm. Yeah. Yeah.
James, you appear to be testing in uncontrolled airspace at this time.
Mm-hmm.
Given you've got ADS-B, and I guess you're targeting operating in a controlled airspace. Because if you continue with that, you still have to, there are still non-ADS-B, people, non-flying equipped aircraft that could transgress your airspace.
Mm-hmm.
Do you know down the place closed to your test line?
We NOTAM everything, but we don't close the airspace, and so we maintain remote observers to make sure that we've got visual as well as those other elements for situational awareness.
It kind of constrains you to even see, at least at the lower level.
With the present equipage, yeah. Mm-hmm.
As you ground-based pilot with the great visuals you described, is that person actually lived down in the controls or just setting a flight path?
So there's 3 modes that you can fly the aircraft that we use primarily at the moment. So there's full manual, which is like direct pilot to control surface. There's a damped mode where you're controlling the rates, so like pitch and roll rates and things like that. And so damped kind of just takes away all the gusts and kind of makes pilot's life easy, but it's still pretty much a direct actuation. And then stabilized mode is the aircraft will keep straight and level, hands off, and so you basically just give it attitude commands. So I want 10 degrees up or 60 degrees bang, and it'll just hold it. And
can you program in a future trajectory to turn?
So so you can program in an autonomous mission as well. So you set waypoints and then it flies between the waypoints. There's also automatic return to home mode. So if it loses link or things like that, it'll come back. Or depending what the recovery methodology we set for the mission, it'll fly to if it loses link, which has never happened, but we've artificially triggered it to simulate and prove that the system works. But the aircraft will then fly back to wherever you say is the safe place to go to and the safe altitude and so on. Yeah. I thought I was going to get grilled. Yeah, Rebecca.
Probably unsurprising that I'm interested in it, but your proposal of 146 is interfacing on the OSO requirements.
Mm-hmm.
I'm really interested in the concept. Is that because the level of detail is good, or is that because the technical knowledge and training that comes under that 146 banner supports it in a way that potentially new entrants would?
Definitely the second one. So, broadly, the OSOs, I think, present reasonable objectives for an organisation to achieve. Yeah. But yeah, I don't talk to other operators much, but from the few that I have, I often get asked questions like, what does 148 mean? I'm like, oh crap, okay. You've got a fair way to go, and but I don't think it's the best for CAA to have to explain that to people. I think CAA should do much higher level stuff. I think CAA makes a better contribution not having to provide that basic level of education, basically. Yeah.
You took the redundancy of the command control system and the redundant evacuation.
Mm-hmm.
The flight control computer.
Mm-hmm.
Is there any level of software integrity, design integrity, design winning commercial integrity level, or is it?
So we do all of that internally. Our kind of highest level principle at the moment is that you can always operate the aircraft manually. So you're never reliant on the flight computer to fly safe, to maintain safety that you need. So now, exactly. The flight computer can completely die, and we can still fly home.
So if radios talking through hardware.
Exactly. Yeah. So if the flight computer shuts down, then the controls that the commands that come into the flight computer automatically bypass it, and it's a fail-safe bypass. Then they go direct to the controls. Yeah, but the flight computer is crazy reliable though. Yeah.
Yourself and with Dawn and certainly Rocket Lab, the scale of what you're doing and the engine technology seems to be the point of difference for both. Is that the case for you? And could you talk a little bit about how you actually get a certification of the engine?
Yeah. So our engine is fundamentally very different to what Rocket Lab operate for many reasons. I mean, one, like we want to fly it thousands of times, and a traditional rocket engine will fail in fatigue after much less than that. But there's other really substantial differences between what we do and what Rocket Lab does. I mean, our ability to recover from anomalies is a really central and important one that is just a completely different scenario. If anything goes wrong on a rocket, it's all over, right? You can't land it, you can't recover it, nothing. You're up in smoke. The aircraft, you can have a lot go wrong on an aircraft, and in the worst case, you do a controlled ditch somewhere that you've established as a safe place to do that. But more likely, actually, you can come and land, and then you can fix that thing that went wrong, and it's not the end of the world. So the technology is fundamentally very different, and from the principles that you apply right down through actually the hardware we develop and so on. But then there's other substantial differences as well, in that the regulatory system is completely different. So as I mentioned, we don't need restricted airspace. We integrate with other air operators, which a rocket does not do, and we use existing infrastructure. There's thousands of airports all over the planet. There is very few launch pads all over the planet, and they're all, except for Rocket Labs, military controlled. So they're really difficult to get access to. So, even if you had this amazing rocket factory that could pump out rockets for free, you couldn't go and launch them all because you don't have the launch pads. And even if you magically go and build a ton of launch pads, which is, very difficult, you still couldn't fly them all because you couldn't get the regulatory approvals to shut down enough airspace to fly them all. A, because that's complicated, and B, because the rest of the aviation system just won't let you because they want to use the airspace as well. So it's completely different. So going back to that competitive assessment matrix, this should not be 20% better than Rocket Lab or 50% better because we've got a better engine. This should be 3 orders of magnitude better because of all of those things, not just technology.
And on that chart, you didn't tell us what your engine used. You had
Yeah, so that was satellite propulsion. So our satellite propulsion uses nitrous oxide and propane. So again, it has to be super scalable to be orders of magnitude better. So propane's in every barbecue on the planet, and nitrous oxide's in every hospital on the planet. So
that's what's going on this.
Nope. So the rocket engine for this is like a version of kerosene that doesn't have all the aromatics and stuff in it, and hydrogen peroxide. So and Rocket Lab is liquid oxygen and the same, more or less the same kerosene-based thing. But that's not that is an important difference because peroxide is storable; it's not cryogenic. Liquid oxygen is cryogenic, which makes it difficult to handle. But yeah, the aspects I mentioned about fatigue and stuff like that, those are also really key differences in our engine design. Yeah.
And then going back to my original question, what is kind of your approach for certifying the engine?
Yeah, sure. So within 102, you select standards, you select design standards, and so there's Rule FAA Part 437, which is suborbital reusable launch vehicles. So that's exactly what we are. That gives you indicative guidance on what other principles or standards or methods you should use. Certainly, we've adopted principles from Part 33 where applicable. Obviously there's not going to be much of Part 33 which is applicable to a rocket engine, but certainly some stuff in there. So it's kind of a 102 tells you to select something and present it to CAA, and if they say sounds good, then you use it. Yep.
So key aircraft is at the moment. Have you controlling sort of the more complex aerodynamic engineering aspects? Have you done any flight analysis or aerodynamic elasticity or?
Yep. Yeah. So we put the whole thing in a supersonic wind tunnel. Done lots of CFD and all that kind of thing. There's mountains of analysis that have gone into this. It's limited by the speed limit of our warranty certificate at the moment by a mile.
Need to get the questions off, but we do need to close our session. But fantastic presentation, James. Thank you very much. I'll back up in saying, my experience with dealing with novice applicants into the system, you should see the looks of some people's faces when they ask, I want to be a 146 and a 1 holder and want to distribute and I want to get the tax certificate. That should be easy, right? A lot of education that's going on, and for those of you that remember David Barrett's discussion earlier about the different technologies unit, that is being stood up to address some of these issues we've been talking about, the lack of awareness of what goes into an aerospace regulatory regime and what compliance looks like. So very interesting proposal in terms of how the 146 community could support those activities. I'd be curious to see, as we go forward, other rules and organizations thoughts on how they want to participate in that aspect. Key thing to keep in mind, I'm not sure if everyone's aware, 102 is considered an operational certificate. It is not a product certificate, so it doesn't hold the same level of authorization, or it's not the equivalent to say a protection or supplemental protection. It is an operational certificate at the end of the day, but as designed, it's very encompassing in terms of the requirements that can be levied. We've had people call the largest exemption we ever produced, because it is kind of, effectively does allow us to bespoke surveys procuring not only on the product side, but the operational side as well. So talking about the home builds, the big difference between home builds, the home builds have two very separate regimes that they have to comply with. There's what they need to do correctly designing the building home build, but they also have a very constrained operational space in the operational rule set that they have to comply with. Whereas 102, it is all scalable based on intended design and intended operation, and that's what kind of forms the sandbox. So,
yeah, thanks.
Thanks,